Hi, today we are going to study about the alternating series. Look through the definition of this. What do you mean by alternating series? Alternating series means series alter its signs. Series together with the sign is altering, that is, the sign is changing. This is the definition. Sigma n equal to 1 to infinity minus 1 raised to n minus 1 an, or sigma n equal to 1 to infinity minus 1 raised to n into an, where an is a positive number. We use the alternating series test to determine the convergence for this series. This is the alternating series test. Alternating series test. If the alternating series is of the form sigma n equal to 1 to infinity minus 1 raised to n minus 1 an equal to a1 minus a2 plus a3 minus a4 plus a5 minus a6 plus etc. which is greater than 0 satisfies the conditions. First one is it must be a decreasing series. An plus 1 must be less than or equal to an for all n. Limit n tends to infinity, an is equal to 0. Okay, limit n tends to infinity, an equal to 0. If this two condition is satisfied, then we can say that the series converges. The series converges. This is a proof of the theorem. We first consider the subsequence S21 comprising even terms only. S2 equal to A1 minus A2, which is greater than or equal to 0 since ANs are A1 is greater than or equal to A2. S4 is equal to this one, which is greater than or equal to S2, etc. This is a term. So the sequence S21 is increasing. Next sequence S21 equal to A1 minus A2 minus A3 this is the expression. Every expression within the parenthesis is non-negative, which is non-negative because an plus 1 is less than or equal to an. So S21 is less than or equal to A1 for all n. That is, the sequence is bounded above. So the sequence is S21 is bounded above and which is increasing sequence. Then we can see that the limit it is convergent and by monotone convergence theorem it is convergent and let it be converges to S. We consider the subsequence the sequence S21 plus 1 comprising the odd terms of S21, and since S21 is equal to S21 plus A21 plus 1 and limit n tends to infinity, A21 plus 1 is equal to 0 by the assumption. So this equal to S21 plus 1 equal to limit n tends to infinity S21 plus A21 plus 1, which is equal to S. So S21 and S21 plus 1 are the subsequence and whose partial sequence or partial sums Sn both converges to S. So the limit Sn n tends to infinity Sn converges to S. So we can say that the series converges. Next is an example. Show that the alternating harmonic series converges. Sigma n equal to 1 to infinity minus 1 raised to n minus 1 divided by n is equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 etc. which is converges. This is an alternating series with an is equal to 1 by n. So we use the series test to verify that an plus 1 is less than or equal to an, which is equal to 1 by n plus 1, which is less than, always less than 1 by n. This is an. So limit n tends to infinity, an is equal to limit n tends to infinity 1 by n, which is equal to 0. So by alternating series, this series converges because this two conditions are satisfied. An plus 1 is less than an and limit n tends to infinity, an is equal to 0. Next, to determine whether the series converges or diverges. This is sigma. First question, n equal to 1 to infinity minus 1 raised to n into 2n divided by 4n plus minus 1. This is minus 1 raised to n minus 1, 3n divided by 4n square minus 1. Since both series are alternating series, we use the alternating series test. An equal to 2n divided by 4n minus 1. And because the limit n tends to infinity, 2n divided by 4n minus 1, that is n is taking outside, so the value will be 1 by 2, which is not equal to 0. So by alternating series, the test is not satisfied. Okay, so this computation shows that the limit minus 1 raised to n, 2n by n 4n minus 1 is equal to, which does not exist, and the divergence of the series follows from the divergence test, because by taking limit of this one, this is not equal to by divergence test, we can say that this does not converge. Next is an is equal to this one. Here an plus 1 is greater than or equal to for an plus 1 by showing that f of x equal to this one. For that f dash x is less than, find f dash x which is less than 0, which is negative actually, less than 0. So we can say that f is increasing. Sorry, f is decreasing. Okay, so limit n tends to n is equal to 0. So by alternating series test, the series convergent. Next is the error estimator in alternating, approximating and alternating series. Okay, so before that we had to do the problems from the exercises. We have to complete that. That is a work. Okay, that is a homework for you. Today I think we can wind up our section because we have to do more problems in the alternating series. Okay, thank you.